Hi everyone, this is Yukabuka and welcome to my home on YouTube. In the first video, we discussed how to set up a Linux ARM64 kernel running on QEMU. And in this video, we will discuss how to debug the Linux kernel that we just set up. And as for what we will be discussing, we will first need to set up a way to share files between the QEMU VM that we just set up and the host machine so that we can write our own programs, compile it, and then run it on the VM. We will write a test program that calls ptrace. We will compile it on the host machine using our cross compiler and then copy it over to the VM. We will run the program, debug the kernel, and intercept that call to ptrace. Alright, let's get on with it. First, we will discuss how we can set up an easy way to share files. If we go to the build root folder that we set up yesterday, we can go inside build root and build root 2016. The first thing to do is to create a folder by the name of build root files or whatever you want to name it as, that will contain all the files that you wish to transfer to the VM. Once you have that folder, in my case it's home, repos, build root files. Once you have such a folder, you edit a config variable inside build root to point to this folder. And the config variable is br2 rootfs overlay. So you just modify this specific config variable to point to the folder that contains the files you wish to transfer to the VM. Let's quit. Let's remove the final output images that were created as part of the previous build. Now let's do a make. This should not take too long because the build has already happened once and it's done. So right now we have built a rootfs image with the files that we wish to transfer over to the VM. Now that that is done, we go over to the folder containing our Linux kernel and perform a quick rebuild. The reason we do this is because if you remember from our first video, we modify a config value at the root of the Linux kernel source pointing to the initramfs that was built by build root. Now that we have modified the initramfs to contain our own files, we tell the kernel to build with the new initramfs, and that is why we are building it again. And now that we've built it, we should hopefully be able to boot the VM and see that these files have been transferred over to the virtual machine. So let's try booting up the virtual machine as shown in the first video. Let's try logging in and let's go to the root folder, and yes, we can see that these files have been transferred over to the VM. So that's a success. Now that we've discussed how to transfer files to the VM, let's look at what files we have transferred. So the example that we have transferred here is rather simple. We don't need this line here. All it does is it causes a fork and the child proceeds to execute a bin ls. while the parent executes a ptrace syscall and intercepts the first syscall made by the child. The reason I wrote this test program is because I just needed something that would invoke sysptrace, a system call that I can intercept while debugging the kernel later on. So this program in itself is not that important. However, you can copy it off the screen if you'd like to. So now that we have everything set up, let's try to debug the kernel and intercept the calls to ptrace. We start off by rebooting the kernel, by bringing up the kernel, and the kernel is brought up by performing this particular command. In this case, you can notice that we specify some parameters related to the type of CPU in these lines. We show that we boot up the kernel using 2 GB of RAM and a path to the kernel image. And $1 and $2 specifies the arguments that I pass to the script. There may or may not be any arguments. The reason I put this in is mainly for convenience. In order to be able to debug the kernel from boot onward, I would need to invoke QEMU system ARC64 with 2 flags, -s and -caps-s, as follows. So /start.sh -s and -caps-s. This will tell QEMU to boot the kernel, but to pause execution at the very beginning and wait for a GDB client to connect to it before resuming execution. So let's try starting this, and we notice that the VM has not started booting yet. This is because QEMU, the GDB stub inside QEMU, is waiting for a GDB client to connect to it. So let's go to on a different terminal. Let's go to the root of my Linux source code, and let's start GDB MultiArc. GDB MultiArc is something you can get through your package manager, such as apt-get or RPM. But please note that you need to be using GDB MultiArc when debugging ARM64 from an x86 or x64 machine. So you started off by passing the flags -q, because, or maybe we don't need the -q for now. Let's just use the verbose output. Let's just use gdb-multiarc /vmlinux. We can see that it's reading the symbols from vmlinux, and we explicitly specify what the target architecture is. In this case, it is going to be set arc ARC64, and it says that the target architecture is assumed to be ARC64, and now we tell it to connect to the port 1234. It's target remote 1234, because when you pass the small dashes flag, it tells QEMU to wait for a GDB client stub at localhost port number 1234. It's a short, so the -s is a shorthand for that. So in the GDB client, when we say target remote :1234, it should be able to connect to the QEMU GDB. Alright, it seems that it says remote debugging using port 1234 and the instruction at this address. So now I hit continue, and we can see the VM boot up in the first terminal. There we go. So the VM boots up as normal, as it does normally. We can log in, we can view the files, go to the root directory. We can see our files in the root directory. Now what I wish to do is to be able to set a breakpoint in this window and execute the binary sysptrace in the first window so that the breakpoint hits in the second window. So in order to do this, I first need to obtain the kernel system call address for ptrace, and I can do this by parsing the file proc_kl_sims as follows. I can do cat proc_kl_sims grep sysptrace, and I have gotten the address of the ptrace system call. Now on window 2, I hit Ctrl+C to pause and interrupt, and I set a breakpoint at the address that I received, the first line over here. The first line over here. I set the breakpoint, and it says that the breakpoint has been set in file kernel ptrace.c line 1078, and I hit continue. Now on the first window, I execute simple ptrace, a binary that causes the ptrace system call to be invoked. In fact, I would use strace, but strace in effect, I would use strace /simple ptrace, but strace in itself uses ptrace, so I don't want there to be a confusion. So in this case, I'm just going to execute simple ptrace. Okay. And we can see here that the breakpoint has been hit. Breakpoint 1 sysptrace request 0, PID 0, ADDR 0, and data is equal to 0. Now it is possible to step through each line of the kernel code. For now, I'm just going to continue. And this is how we can debug the Linux kernel. We can see that if you provide the VM Linux file to GDB MultiArc, it is possible to debug the Linux kernel at a source level. Please note that the source level debugging is a bit risky in cases where functions may be inlined. However, in a lot of cases, it makes the debugging experience a whole lot easier. So now that we know how to set up debugging on this VM, that's it for this video. As always, hit like if you've learned something new from the video, and hit subscribe if you'd like to be notified of new ones.